Now let's see the properties of Dirac delta function. Okay, we will discuss some properties of Dirac delta function. The first one is the delta minus x, that is equal to delta x. Okay. Then second one is x delta x equal to 0. These two are actually very trivial properties. It is quite obvious from the definition. If you put minus x instead of x, you will be getting in the expression for delta x, you will be getting delta x itself. So delta minus x is delta x. It's an even function. Another thing is x delta x 0, that is so obvious, since we know the delta x is, we all know delta x is equal to 0 when x not equal to 0. Okay, so if you multiply x with delta x, it will be 0 everywhere x not equal to 0. At x equal to 0, since we are taking x delta x, this will be equal to 0. Okay. So these two properties are very straightforward. Then we see a third property, the delta ax. Delta ax, a is some constant, that is equal to 1 by magnitude of a or modulus of a delta x. We look at the proof of this. Consider integral minus infinity to plus infinity delta x f of x dx. Here let me put y equal to x. Then dy will be a dx. Dy will be a dx. Okay. So this integral, that will be transforming into integral minus infinity to plus infinity delta y f of y by a, because x is y by a. Okay, x is now equal to y by a. So f of y by a dy. Dx is dy by a. So that a comes here. Now by the property of the Dirac delta function, we know this will be equal to 1 by a f by 0, because we know integral minus infinity plus infinity f of x delta x dx, this is equal to f of 0. So by that property, this will be equal to f of 0. So we get this expression. So that is when a is greater than 0. And if we consider a less than 0, suppose that we consider a less than 0, a can be less than 0. So y equal to x can be negative, or y equal to x, that will be negative depending upon the value of x. Okay. So what we do is, we write y as equal to minus of modulus of a x Okay, we write y as equal to minus of modulus of a into x. Okay, and here since y equal to minus x, when you write into this function where y f of y by a, for f of x we are writing f of y by a. Since the negative is there, you change the integration limits from minus, originally it is from minus infinity to plus infinity, that you change from plus infinity to minus infinity. Okay, so here you can see plus infinity and minus infinity. Okay, so delta y f of y by a. For dy, for dx we are writing dy by minus of modulus of a. Okay, then here we are writing this as this negative sign here, that changes the integration limits from plus infinity to minus infinity to minus infinity to plus infinity. Okay, so we have this 1 by modulus of a integral minus infinity plus infinity delta y f of y by a dy, and this term that is equal to f of 0, that is f of 0. So we will get 1 by modulus of a f of 0. Now combining the results, this result plus this result, we write the minus infinity to plus infinity delta x f of x dx, that is equal to 1 by modulus of a f of 0. And f of 0, you know, that is this, what, minus infinity to plus infinity delta x f of x dx. So if you compare this and this, you compare this term and this term, you get what? The delta x as equal to 1 by modulus of a delta x. Okay, so you get this property of the Dirac delta function. Now we are taking the derivative of the delta function. Okay, the derivative of the delta function, and the derivative of the delta function or the delta function relation have only meaning through their application within the integrals. Okay, so we can say here suppose I take minus infinity to plus infinity f of x, the derivative of delta x, d by dx of delta x, which is taken as delta prime of x. Okay, delta prime of x dx. Okay, d by dx of delta x. Now what we do is we do the integration by parts. So we write this in this form. So we get what, by integration by parts we will get delta x f of x. Here limits are minus infinity to plus infinity, then minus integral minus infinity to plus infinity delta x f prime of x. Okay. Now this term is 0 because when you apply the limits, you know, at x equal to minus infinity and x equal to plus infinity, delta x is equal to 0. We know this. At x equal to minus infinity and x equal to plus infinity, delta x equal to 0. So this term becomes 0, and here this term is f prime of 0, because what we have is f prime of x. This is f prime of x, so we will have f prime of 0 here, so minus f prime of 0. So we get what? Integral minus infinity to plus infinity delta prime of x f of x dx is equal to minus f prime of 0, and this property is known as the shifting property of the Dirac delta function. Okay, so minus infinity to plus infinity delta prime of x f of x dx, that is equal to minus f prime of 0. Okay, so if you take this integral with a function f of x, you will be getting the negative of the derivative of the function at x equal to 0. Okay, so this is actually called the shifting property of the Dirac delta function. Another interesting thing is if you take minus infinity to plus infinity x delta prime of x, okay, you are taking minus infinity to plus infinity x delta prime of x dx. Again, by integration by parts, you will have this, what, x delta x minus infinity to plus infinity, then minus integral minus infinity to plus infinity delta x dx. As we saw earlier, this term is 0. Okay, I need not again say why it is 0. At x equal to plus infinity and minus infinity, delta x is 0. And this term, you know, this is minus 1, because the integral minus infinity to plus infinity delta x dx is the area, the property area, and we know for the Dirac delta function the area is equal to 1. So we will be getting what, minus 1 here. So these two are equal, this one and this one, these are equal. Okay, so that equality is written here. Now when you compare, we will get x delta prime x equal to minus delta x. You will get x delta prime x equal to minus delta x. So these are the properties of the derivative of the delta function. Okay, now let's look at the three-dimensional Dirac delta function. Three-dimensional Dirac delta function, it is defined as delta r. This is three-dimensional Dirac delta function. This is equal to delta x, delta y, delta z. So product of delta x, delta y, delta z. We have already seen delta x. This is the one-dimensional one. Okay. This is the one-dimensional one, delta x. For the three-dimension, we have delta x, delta y, and delta z. So this is our delta r. And what are the properties? As we had in the one-dimensional Dirac delta function, the properties are, the first one is this, delta r, this is 0 for r not equal to 0, and it is infinity for r equal to 0. So this property we had for the one-dimensional Dirac delta function. And the third one, the second property is, along with this has to satisfy the minus infinity to plus infinity delta r d tau. This is equal to 1. Okay, for one dimensional also we had this one. And this d tau, this is Wholly element, that is dx dy dz. Okay, dx dy dz. This is our d tau. So these are the two properties it has to satisfy. The first one is this delta r 0 for r not equal to 0, delta r equal to infinity for r equal to 0. Okay, and along with this has to be satisfied. Integral delta r d tau equal to minus infinity to plus infinity. Three integrals are there: delta x, delta y, delta z into dx dy dz equal to 1. And as we had in the case of one-dimensional Dirac delta function, here we have this equation. What is it? Integral delta r f of r d tau. This is equal to f of 0. Okay, this we had seen in the one-dimensional Dirac delta function as well. Integral delta r f of r d tau, that is equal to f of 0. Okay. Another interesting thing is integral f of r. See, integral f of r delta r minus r 0 d tau, that is equal to f of r 0. Okay. This also we had the integral f of r delta r minus r 0 d tau, that is equal to f of r 0. Okay. So here as we had in the case of delta x minus a, the properties are like this: delta r minus r 0, this is equal to 0 for r not equal to r 0. Okay, and this delta r minus r 0, that is equal to infinity when r equal to r 0. Okay. So that expression, and using that we can write integral f of r delta r minus r 0 d tau, that is equal to f of r 0. Okay. Another interesting thing is we had given an expression or a representation of delta x. Delta x we know that is 1 by 2 pi integral minus infinity to plus infinity exponential I k x dk. This is the integral representation of the Dirac delta function. Okay, and delta x equal to 1 by 2 pi integral minus infinity to plus infinity exponential I kx dk. And the thing is here we need three-dimensional one. So what we have is, for delta x we have this expression, for delta y we will have this same kind of expression, delta z also we will have the same kind of expression. So you combine this delta r we know. What is delta r? Delta r is delta x, delta y, delta z, isn't it? So as you multiply, and if you represent delta x, delta y, delta z in this form, what you have is this, or this one, 2 pi to the power minus cube integral exponential I k x x k y y k z z, okay, dkx, dky and dkz. And if you combine, if you write this in this form, k dot r, k we know the components are kx, ky, kz, r the components are x, y, z. So when you take k dot r, you will be getting kxx, ky, kz. So you will be getting, or you can express this in this form. Delta r is equal to 2 pi to the power minus 3 exponential integral exponential I k dot r and d cube k. So this is how we represent the Dirac delta function in 3-dimensional form. Okay.